Welcome to section 3.3, Piecewise Defined Functions. In this section, we are going to be using some of the functions that we have gotten practice graphing, some of our basic functions and transformations from the previous two sections. The only new idea in this section is that of breaking up a function into several different pieces. Now sometimes you'll have situations that simply cannot be described by a single formula, and that's where piecewise defined functions come in. If you consult the notes on page 43, you'll see that we don't really have a specific definition of a piecewise function, and that's because there really isn't one. There's a description of what it does and why we might need it. And here on the page we see an example of a piecewise defined function. So what this function does is if we plug in a certain x value, we check whether it's less than 1 or greater than or equal to 1. If it's less than 1, we'll plug it into the top formula to find y. If it's greater than or equal to 1, we'll plug it into the bottom formula to find y. So we can come up with a table. If I plug in a few x values, we can kind of see what this looks like. And I'll go pretty far back. Alright, if I start at -3, well, -3 is less than 1, so I'll plug that x value into the top formula. 3 times -3 minus 4 equals -9 minus 4, so -13. Let's do the same with -2. Well, -2 is still less than 1, so we'll plug it into the top formula again. That would give me -6 minus 4 for -10. So -2, -10. -1, again, still less than 1. So that would give me -7. 0 is still less than 1, so 3 times 0 minus 4, -4. Now as soon as we plug in 1, well actually let's see what happens with a half. So 1/2 is a value less than 1, so 3 times 1/2 minus 4. Well, 3/2 minus 4 would be 3/2 minus 8/2, so -5/2. I could plug in a quarter, or an eighth, or a 16th, or anything, any fraction less than 1, and I would get my y value by plugging that value into the top formula. So anything up to 1, I plug into the top formula. As soon as I get to 1, I'll plug that into the bottom formula, since 1 is satisfying this second criterion. So -1 plus 2 would give me 1. 2 is also greater than or equal to 1, so -2 plus 2 equals 0. 3 -3 plus 2 equals -1, and so on. So we get all these points to 0, 3 -1, 4 -2, and we can see that that behavior is going to continue. All of the points to the right of 1 are going to lie on the line -x plus 2. And all of the points to the left of 1 are going to lie on the line 3x minus 4. So generally speaking, you don't really always need to come up with a table. So if we want to graph a piecewise function, all that we really need to do is figure out what each of the pieces should look like, and then only graph them where we're supposed to. So I like to visualize what I'm doing with the plane. So if I divide the plane into the sections where I'm going to have all of these different pieces, I'll do that very softly. So at x equals 1, that's where things change. Anywhere to the left of 1, my graph should look like the top line. Anywhere to the right of 1, or at 1, my graph should look like the bottom line. So from here over, we're going to graph negative x plus 2. And in this direction, we're going to graph 3x minus 4. Okay, so let's start with the left-hand side. 3x minus 4, I could plot all of these points that we found, but I'm going to do it using the theory of what that line should look like. We'll have our y-intercept down at negative 4, and we have a slope of 3, so if I rise 3 and run 3, oops, I'll hit the line beyond which I'm no longer supposed to graph 3x minus 4. But that gives me an idea of the direction it's going, so anywhere to the left of that line, that's what my graph should look like. And I'll put an open circle there because when x is 1, we're no longer supposed to graph the line 3x minus 4. So we get to that point, but we get very close to that point, 1, negative 1, but we never quite get there, since as soon as x equals 1, we jump to our other line, which let's now graph. So that line would have its y-intercept at 2, so I'll put a little open circle there at 2 just to help me graph this. And this one has a slope of negative 1, so if we fall 1 and run 1, that'll put us right there on the line. That's our point 1, 1. If we fall 1 and run 1 more, that'll give us another point. So the y-intercept of this line doesn't actually get graphed. It's not actually part of the function f of x. I just put it there to kind of help me see where this line should be. So everything here that's solid, that left-hand piece and this right-hand piece, this describes what this function does. This is the graph of f of x. Now the more practice you get, you will not need to draw this vertical dotted line. It's just there as a visual guide. I sometimes will overlay a piece of paper vertically at the x values where my function's pieces begin and end. You can do the same, or as you get more practice, you'll start to see where those pieces should go. Here we see another piecewise defined function, f of x. This one has slightly more interesting pieces. The pieces of the last function we saw were both linear. This one has a piece which is going to be based on our x squared graph, and a piece which is going to be based on our square root of x graph. Now, where are each of these occurring? Well, anywhere to the left or on the y-axis, we're going to graph x squared, and anywhere to the right, strictly, of the y-axis, any positive x values are going to get plugged into the square root of x, and that will determine the y values. So if I set up my axes, this is where it comes in really handy knowing exactly what the graphs you're basing this off of look like. We'll graph the piece to the left or on the y-axis first. So anywhere to the left of the y-axis, here we have negative x values or 0. We're going to graph x squared. And anywhere to the right, we're going to graph the square root of x. Okay. Now, the graph of the x squared function contains the point 0, 0, contains the point negative 1, 1, negative 2, 4, negative 3, 9, And that's about all I have room for, so I'll connect those up. Okay, that's our first piece taken care of. Our second piece looks like the square root of x. Now the square root of x normally starts at x equals 0, but since we're not supposed to graph that piece until we are to the right of 0, we're going to put an open circle there just to help us graph. But as soon as we get a bit to the right, we see the point 1, 1, the point 4, 2, the point 9, 3, and we know the basic shape of it looks similar to x squared, but in this case kind of throws out to the side rather than upwards. Okay. So there we have x squared when x is less than or equal to 0, and here we have the square root of x when x is greater than 0. Now it turns out that our function pieces actually join up. They meet here at 0. If we had plugged x equals 0 into either one of these pieces, we would have gotten the same y value of 0. So since when I'm all done with this graph, I could trace along it without ever lifting my pen, this graph we would say is continuous. So it's a continuum. It does not disconnect at any point. But looking back at the first graph that we looked at, we can see that the pieces, if I wanted to try to graph these guys, the left-hand piece and the right-hand piece, I could graph the left-hand piece up to that endpoint. Then I have to lift my pen to get onto the other line and continue graphing my function. So this gap here between the two pieces means that this function is discontinuous. So we have those two ideas of a continuous function and a discontinuous function. This is the first time we've really talked about that, but we have seen functions with discontinuities before, functions where all of their pieces cannot be connected with a single pen stroke. Finally, here we see a piecewise defined function f of x, which has 3 pieces. So there is no real limit, theoretically, on how many different pieces your function can have and how many subdomains, how many portions of the domain you break it up over. We won't see anything much more extreme than a function with 3 pieces, but I wanted to show you guys what that would look like. Now, I'm going to do this one a little bit differently since these functions are a little bit trickier to graph. So I just want to make sure we are solid on what each piece should look like, and then we'll combine them into our final picture. So our first piece, 1 over x, passes through the point 1, 1, 2, 1/2, 3, 1/3, and so on, and has that nice curvy shape to it. So there we have the first portion of the graph of 1 over x. And to the left, it passes through the point -1, -1, -2, 1/2, -3, 1/3, and so on. -1/2, -2. This is an odd function, and I don't mean that it is strange. I mean it is symmetric with respect to the origin. Okay, so one of our pieces is going to look in some part like the graph of 1 over x. Our second piece y equals x cubed minus 3, we're going to use transformations of functions to move the graph of the cube function down 3 units. So here we see the cube function. Outside of that I'm subtracting 3, so I'll move it down 3 units. Now our cube function passes through 0, 0, 1, 1, 2, 8, pretty extreme graph. And this one is also symmetric with respect to the origin. So reflect all of those points and connect it all up. So our graph is very steep, not quite vertical, but pretty close. Then we're going to shift that down 3 units. So the graph that we actually want is going to be over here. If I go 1, 2, 1, 2, I may not be able to see all of the pieces, but we're going to shift these 3 at least down 3 units. So 0, 0 is going to move down to 0, negative 3. 1, 1 is going to move down to 1, 0. Oh, sorry, we're moving down 3 units. Correction there, that one's not the point. And our point negative 1, negative 1 will also move down 3 units to land at negative 1, negative 4. So there we have the graph that we are actually going to copy a portion of for the final function. Our last piece will graph 1/3 x, and that one is just going to be a line with the slope of 1/3 passing through 0, 0. Another way to think of that is the identity function. Here we have x, and we're multiplying that by 1/3. So we could think of this as scaling our most basic of the basic functions and compressing it by a factor of 1/3. So if I plug in x, I'll get 1/3. If I plug in 1, I'll get 1/3. 2, I'll get 2/3. 3, I'll get 1. So there we have the rise of 1 and the run of 3. And that's our graph. Okay. Now I'll copy all of those pieces together onto my final graph to arrive at the graph of f of x. So this one is a bit complicated, and you want to be very meticulous with all of those points to make sure we end up with exactly the right picture. Okay, so where are we going to put the pieces? Well, to the left of negative 1, we're going to graph this guy. So if I plot some x values along the axis, alright, got our y values. So to the left of negative 1, I'm going to graph 1 over x. Between negative 1 and 1, I'm going to graph that second one we came up with, the transformation of the cube graph. So between negative 1 and positive 1, we're going to graph x cubed minus 3. And beyond that, for x equals 1 or greater, we're going to graph 1/3 x. So you don't need this stuff at the bottom. This is just kind of a nice way to help you keep track of where everything should go. Alright, so at x equals 1 our negative 1. We're going to have one graph to the left of that and one graph to the right of that between negative 1 and 1. And then another graph to the right of positive 1. So, the portion of 1 over x that I want is just going to be that little tail that starts at negative 1, and goes off to the left from there. So I'll put an open circle, negative 2, 1/2, negative 3, 1/3, negative 4, 1/4, and that's our first piece. Took care of the first region. Now in the next region, we are going to take everything at negative 1, so that point, up to positive 1, but not including. So we're going to graph that point, everything in between, and have an open circle at that other end. So where was that first point from left to right? Since we kept track of all of these points in our original transformation, that point is going to be located at negative 1, negative 4. So I'll put a closed circle there. That's the first point that lies on this piece. Then we are graphing the cube root function. It passed through 0, negative 3. And curves in this fashion till we get to x equals 1, where our function is no longer going to be describing the behavior of f of x. When x equals 1, remember we have 1, 1/3. So now we're going to graph y equals 1/3 x everywhere to the right of 1. 2 2/3, 3 3/3, 4 4/3, and so on. So there we have 1 over x in the region where it's supposed to occur. Here we have x cubed minus 3 in the region that it is supposed to occur. And here we have 1/3 x in the region in which it is supposed to occur. Now, you want to always make sure that these functions with the funny endpoints pass the vertical line test. So notice that this piece, the first piece, based on 1 over x, has an open circle, and x cubed minus 3 has a closed circle at that x value of negative 1. So my function passes the vertical line test even at that x value. And then it passes the vertical line test along x cubed minus 3. And then again I have an open circle on one piece because I have a closed circle on another piece. So that still passes the vertical line test, and this is my graph of f of x. Again, we are seeing two gaps between the pieces that we graphed, so I would have to lift my pen twice if I wanted to draw this graph from left to right, so this is a discontinuous function. But that's not something that we're going to have to worry too much about. It is a good definition to start to notice when functions are continuous or discontinuous. That becomes a bigger deal later on in the math curriculum. But that is the general idea behind piecewise functions. Now, how you go about graphing them is entirely up to you. Sometimes it's a good idea to graph each piece in its entirety and then only copy down the portion satisfying your boundary criteria. Sometimes for the simpler ones, like the first one that we saw, we can just divide the plane and go ahead and graph in each portion of the plane and only graph what we really need to pretty easily, especially when we're talking about lines. So this section is really going to rely on your comfort with those basic functions and comfort with graphing lines very easily and quickly, even if you aren't necessarily supposed to include the y-intercept. And just like any other type of function, if you ever get stuck, you don't remember what the graph looks like, you can always come up with a table of values. Now for the more complicated piecewise functions, you're going to want to use a lot of x values, inputs, in order to see the shape, the curvature of each piece. This one, for instance, would have been quite a bit of work, but you can always do that. So that is all that I would like to go over for this section. Go ahead and get started on those homework problems and bring any questions that you have to class.